Hi everyone, welcome back to the channel. Today we are diving into the exciting world of reinforcement learning, specifically exploring a powerful new algorithm called Group Relative Policy Optimization or GRPO. So by the end of this video, you will understand how GRPO is reshaping the way we train advanced LLMs. So this video is divided into three parts. So first, we'll explain the concept clearly, and the second part, we're going to build a Python script that train a model that fine-tuning a model using GRPO with UnSloth. And in the last part, we're going to test and analyze the script logs. Why GRPO? Let's say that GRPO is particularly special because it provides stable and efficient training by evaluating multiple responses simultaneously, and is famously used by the leading AI models like Deepseek's R1 for its remarkable reasoning capabilities. So let's start simple. Image training a dog. When it sits after you say sit, it gets a treat. If it doesn't, no reward. So over time, the dog learns sitting equals to rewards. That's reinforcement learning in simple words. But instead of a dog, we have an AI model called agent. And instead of treats, we have numerical rewards. There are 5 key components you need to understand. First of all, the agent. This is our learner, in our case, an AI model. The environment where the agent interacts and learns from. Actions that are basically choices that agent makes. The rewards that are positive or negative feedback from the environment. And the policy that is the strategy that the agent uses to choose its actions. So actually the agent observes, takes actions, gets rewards, and updates its policy, continuously improving through trial and error. But why does this matter for large language models? LLMs learn initially by predicting the next word in sentences, but this is enough. We want our models to be helpful, harmless, and aligned with human preferences. So reinforcement learning helps fine-tune this model, teaching them to respond better according to human feedback. So one popular method is reinforcement learning from human feedback, or RLHF. Humans choose preferred response from the AI. We train a reward model based on these human choices. The LLM learns to produce responses that this reward model ranks as best. This brings us to GRPO. It improves on previous methods like PPO and DPO by grouping responses and comparing them together instead of individually. This group-based approach creates more stable learning and helps model converge faster and more reliably. So how does GRPO work? GRPO has 3 main steps. The first is the group formation. So the model generates multiple solutions for each prompt, like a student trying several approaches to a math problem. And then there is the preference learning. So each response gets scored. And at the end, we have optimization. So the model updates its strategy, encouraging good solutions and discouraging poor ones. So if you want to get deeper about the GRPO algorithm, you can visit a Hugging Face page that is really complete and really clear, and it will teach you the math behind the algorithm. You can find directly in LLM course in Hugging Face. Let's dive deeper into the GRPO algorithm. The core innovation of GRPO is how it evaluates multiple responses simultaneously, rather than relying on a separate reward model. Here's how it works in detail. Step 1 is the group sampling, that actually the model generates multiple answers for a single prompt, creating diverse responses for comparison. For example, solving 2 plus 2 multiplied 6 might yield a correct answer like 14 and incorrect ones like 10 or 16, for example. The second step is the advantage calculation. So responses are scored. GRPO uses a relative advantage. So the advantage, as you can see in this formula, actually is a response score minus group average and divided by the group standard deviation, okay? The positive advantage means that the response is above average and its likelihood will be increased. Negative advantage indicates poorer than average performance. So we go on the step 3, that is the policy update. So GRPO updates the policy using these advantages combined with the probability ratio. That is you can see this complex formula, but actually we can divide in 3 parts. So we have the probability ratio, that is just new versus old policy probabilities. The clipping function, that actually limits extreme updates, and the KL divergence, that ensures policy doesn't drift drastically. So this ensures stable and meaningful improvements over iteration. So this is just the core to update the model weights. So image teaching a model to calculate math problems, that actually is our example. We're going to see this Python script that use math problems. So first of all, it produces several answers, some correct, some not. It scores them and learns which method works best. And over time, the model increasingly chooses the better answers. So GRPO actually is changing the way we train AI, so making models smarter, safer, and more helpful. It's already powering top-tier AI like Deepseek L1, Google's Gemini, and even OpenAI GPT-4. So this script is designed to fine-tune a language model, specifically Google's Gemma 3 1 billion parameters IT, to improve its mathematical reasoning capabilities. It uses the GRPO along with the low-rank adaptation, that is LoRA, to efficiently train the model on the GSM-8K dataset, which is a collection of grade school math word problems. So the core idea is to teach the model not just to give an answer, but also provide a step-by-step reasoning process, much like how a student would show their work. So to ensure the model follows a specific structure for its response, we'll guide it to output its reasoning and answer within XML-like tags, reasoning and answer. Let's talk about the underlying principle. We are using LoRA, that is the low-rank adaptation. That basically means that training the entire LLMs is computationally expensive. So LoRA is a parameter-efficient fine-tuning technique. So this drastically reduces the number of parameters that need to be updated, making fine-tuning faster and requiring less memory without sacrificing much performances. We already talked about GRPO. I don't need to explain again the underlying theory. We are going to see better in the script. And we're using the chain of thought prompting. So the script encourages the model to produce a reasoning process before the final answer, that is here. This is a form of CoT, where asking for a step-by-step thinking process often leads to more accurate results from LLMs, especially for reasoning tasks. So the XML tags help structure this CoT. We use UnSloth, that is a really good library, usually used to speed up the fine-tuning process and reduce memory usage, making it feasible to train powerful models on consumer-grade hardware. It optimizes actually the parts of the model loading and training. Let's dive into the code. We have all the import here. We are going to specify some parameters. The first one is the max sec length. Actually, these define the maximum number of tokens, words or subwords, that the model can handle for a single input sequence. This includes both the user prompt, the question, and the model's generated completion, reasoning plus answer. So think of this as the maximum number of words allowed in a short essay. We have the rank, okay. We fix at 32. This sets the rank of the LoRA adaptation. In LoRA, the original weight matrices of the model are frozen, and two smaller matrices whose product approximate the change we want to make to the original weights are trained. So the rank, here 32, determines the size/complexity of these smaller matrices. A smaller rank means fewer trainable parameters, leading to faster training and less memory, but potentially less expressive power for the adaptation. So 32 is a common choice. We have the max prompt length, specifies the maximum number of tokens allowed for the input prompt we're using GRPO. The remaining tokens up to max sec length is actually 1024 minus 256, that is 768. So are available for the model generated completion. We have the system prompts. This is crucial. This is the crucial piece of text. It's a system-level instruction given to the language model to guide its behavior. It strictly defines the output format. So the model must use reasoning tags followed by answer tags. It emphasizes no extra text for deviations, okay, in this part. It also gives a hint about the answer format. It should be a number, and units should be included if the question requires them. So why it matters? This concept defines the key parameters for the model and the training process. So the system prompt is particularly important as it's our primary way of instructing the model on how to structure its responses. So this explicit instruction is a form of prompt engineering. Okay, let's see how to prepare the modeling. In this part, we are going to load the model and the tokenizer. This line loads the pre-trained language model and its associated tokenizer. Here we specify the base model we are using. The max seq length passes the previously defined maximum sequence length. Load in 4-bit, we put it through. This is a quantization technique. Actually, it loads the model weights using only 4 bits per parameter instead of the usual 16 or 32 bits. This actually reduces the model's memory footprint roughly by 4 times compared to 16-bit, making it possible to run larger models on GPUs with less VRAM. The fast inference actually enables UnSloth optimization for faster text generation inference. This might leverage technologies like VLLM if available. We apply the LoRA rank. It informs actually UnSloth about the maximum LoRA rank we intend to use, allowing it to optimize memory allocation. And we have the GPU memory utilization, 0.6. Actually tells UnSloth to try and limit GPU memory usage to 60% of its capacity. This can help to prevent out of memory, especially when other processes might also be using the GPU. And we have the tokenizer that actually is responsible for converting text into a sequence of number tokens, of numbers, actually tokens, that the model can understand, and vice versa. We apply the LoRA. We apply the LoRA in this part. So this function actually modifies the loaded model to prepare it for LoRA fine-tuning. And PEFT stands for parameter efficient fine-tuning. Okay. We apply the LoRA rank, the target modules. This is a crucial parameter. It specifies which layers of the original model will have LoRA adapters applied to them. So the name like QProj, KProj, or VProj, or O refer to the projection layers within the transformer architecture's attention mechanism. And the gate, up or down, refer to layers with the feed-forward network parts of the transformer. By targeting these specific layers, we aim to adapt the model's core processing capabilities. We have LoRA alpha, and we put the same as LoRA rank, is a scaling factor in LoRA, setting it equal to R is a common practice actually. It can be thought as a learning rate for the LoRA adapters. We use the gradient checkpointing that is UnSloth. Gradient checkpointing is a technique to save memory during the training by recomputing some values during the backward pass instead of storing them all. So UnSloth provides an optimized version, and this is especially useful for long sequences or large models. The random state sets a seed for random number generation. This helps to ensure that if you run the script again with the same setting, you get the same results, which is important for reproducibility. So actually this section sets up the core of our fine-tuning process. We load a powerful base model, make it memory efficient, using 4-bit quantization, and then apply LoRA so we can fine-tune it effectively without needing massive computational resources. So the choice of target models directs where the fine-tuning will focus its efforts. We go to the next section, that is the data preparation. We have some helper function. It's an extract XML answer. So this function is designed to extract the content from answer. This other function actually is applied to GSM 8K the dataset originally provides answers in a format like the final answer is new line and the hash, this function extracts the number part. We also have this other function that is the get GSM-8K questions. So this function loads and preprocesses the GSM dataset. This part data actually loads the specified split, train or test of the OpenAI GSM-8K dataset. With the map, actually, here we apply a transformation function to each example in the dataset. So the prompt creates the input prompt for the model. This is structured in a chat format which instruction-tuned model like Gemma expect with a role, system, or user. The last part, extract hash answer, actually extract the ground truth numerical answer from the dataset. So the purpose is to prepare the training data in the format required by the GRPO trainer. So a prompt, which is a list of chat messages, and an answer that we call gold standard answer for the question. we call the function here. Let's go to the most important part, that is the reward functions with the bug prints that help us to understand what happened during the training. So this is a very important section actually, as the GRPO relies on reward functions to guide the learning process. The model will generate several responses, and these functions will score how good each response is. Okay, we start analyzing the first reward function, that is the correctness reward function. We have some parameters here. Actually, this is the primary reward function that tells the model how accurate its mathematical answer is, considering both numerical value and units. So the detailed print statement are here, and actually is really good to monitoring the training process. We have, as you can see here in the function, we have a string similarity, so the helper function that calculates the similarity ratio between two strings, A and B. Extract between actually is another helper function that extracts the text between started meters. We have the main loop here that iterates through each set of model generation gen list and its corresponding gold answer, gold. We get the full here, so it takes the first generation for the current prompt. Actually, GRPO typically involves multiple generations. This might be simplified here, with gen list might represent the top generation after some initial filtering not shown. So we have the reasoning here, we have the predicted answer, and we are going to calculate the final content score in this part. So what happened here? It first tries to parse numbers from both the predicted answer and the gold answer, okay? So we have num patterns here. If both, okay, and red and gold contain numbers, it calculates the numerical score based on a relative error that is max 001 minus the relative error here. And if then tries to extract and compare units, okay? And if numbers actually cannot be extracted from both, content score will be a default to the direct string similarity between red and gold. And we also have try except block here. And at the end we calculate reward, okay? But reward here, we have some debug prints. And here we go. We have other function. We also have another function that provides a small incentive for the model to produce answers that are purely numerical integers. This might be useful for certain types or problems or as shaping a reward. However, it might conflict with the correctness reward function if units are expected. The GSM-8K dataset often has integer answer, so this might be a gentle nudge. We have the strict format reward function, and this function strongly encourages the model to adhere to precise XML and new line structure specified in the system prompt. So this is the key to reliable parsing of the output. We have the soft format reward function. This provides a gentler reward for getting basic tag order right, even if the new lines or surrounding texts are perfect. It can act as an intermediate step towards the stricter format. We have the count XML. This function provides actually a granular reward or penalty based on the precise count and placement of the XML tags and associated new lines. It also actively penalizes superfluous text, penalize any superfluous text that after the final answer tag, which is critical for ensuring the output matches the system prompt. So the script uses a combination of all these reward functions. This is a powerful aspect of GRPO. Some rewards focus on the correctness of the content, while others focus on the structural integrity and formatting, and some on specific content properties. Of course, you can customize this function as you need for your specific case. The trainer, anyway, will combine these rewards, directly during the training, and likely by summing them or using a weighted sum through the exact combination mechanism is a part of GRPO trainer, its internals or default behavior. So to get, at the end, you get a final score for each generated response. And here we go. We will put all the function trainer here. But first we have to actually configure and initialize the GRPO trainer here. Let's talk about the parameters. So it creates an instance, of the config to hold all the hyperparameters and setting for the training process. The learning rate here, both AD and beta are parameters for the Adam optimizer. These are typical default values. We have the weight decay and the warm-up ratio. The weight decay actually is a regularization technique to prevent overfitting by penalizing large weights. The warm-up ratio 0.1 is also default value. For the first 10% of training steps, the learning rate will gradually increase from 0 to the learning rate. So this helps stabilize trainings at the beginning. We have the scheduler type. We use cosine. It specifies how the learning rate should change after the warm-up phase. A cosine scheduler gradually decreases the learning rate following a cosine curve. We have the optim. We use paged Adam 8-bit. It uses actually a 8-bit paged Adam optimizer, which is memory efficient. The logging steps, just how often to log training information, like loss or rewards here. It's every steps actually. Per device train batch size is the number of training example to process on each GPU per step. A batch size of 1 is common when VRAM is limited or sequences are long. We have gradient accumulation steps here. If these were bigger than 1, gradients should be accumulated over multiple small batches before an optimizer step, effectively increasing the batch size without increasing memory. Here it's 1, so each batch is processed independently. Num generation 6, actually this is the core. For each prompt in a batch, the model will generate 6 different completions. This completion will then be evaluated by the rewards function, as we just saw in the upper part. This is a key parameter. We also have max prompt length, max completion length, max steps, that actually the total number of training steps to perform, save steps, how often to save a model checkpoint. We have max grad norm, this line, that is the gradient clipping. If the norm, that is the magnitude of the gradients, exceeds this value, they will be scaled down. This helps prevent exploding gradients and stabilizes training. This is a really important report to known. It means that disables reporting to external services. And we have the output there. We call it outputs. It's the directory where training outputs like model checkpoints will be saved. We have the trainer, and it initializes the GRPO trainer, which orchestrates the GRPO fine-tuning process. We pass the model. We pass the tokenizer. We have a list here of the reward function we defined earlier. The trainer will use these to score the num generation completions for each prompt. The order might matter if the trainer processes them sequentially or combines their output in a specific way, but often they are summed. We have the args, the training args, and the training dataset here. So this section configures actually all aspects of GRPO. We go to executing the train here, the single line that kicks off the entire training process. So just to remind you, each step, it takes a batch of prompts For each prompt, it has the model generate num generation, in this case 6 different completions. Each of these completions is then passed to the reward functions. Rewards from this function are likely aggregated, summed. Based on these rewards, the GRPO updates then the model policy, okay, the trainable LoRA weight, actually, to encourage generation that receive higher rewards and discourage what? Those with lower rewards. And then the optimizer updates the way using the calculated gradients. And at the end, we have the logging, do the logging steps, and prints in reward function will occur showing process. So we have the chat input here, prepares the test prompts in the same chat format used during training. Tokenized false actually return the formatted prompts as a single string. And add generation prompt we put through actually appends the necessary tokens, text, signals to the model should be start generating a response. We have a sampling params here, defines the parameter that control how the model generates text, just a sampling strategy. And then we have the output. So it's time to launch the script, and we can see all the logs, and we are going to start the training. We already activate the virtual env from Python and just launch the Python main py. Some UnSloth logs. Here we go. It's starting to generate some answer, as you can see here. The first GRPO step, the question is here. A concert ticket cost $40. So Mr. Benson bought 12 tickets and received a 5% discount for every ticket bought that exceeds 10. How much did Benson pay in all? So we have the reasoning here. We have the predicted answer, and actually the gold answer is quite good. That's why at the end we have a content score really high, almost 1. Here it's 0.993, and the reward is the content, is the double content. The next GRPO step, actually here the score is really low because the predicted is much lower than the correct one, 34 compared to 476. And here we go. As you can see, the system prompt is quite good because the model is producing actually the reasoning in a really good format within the text. So we can see here, we have the predicted answer, the gold answer, and here we go. Many other math problem that is solving, and at the same time is getting the rewards depending on the answer. And we can see also at the end we have also the other reward function, the soft format, the street format, and the int reward. Another reminder that actually this script required a GPU enabled machine. I'm using actually an AC2 instance from AWS in this case, that I think is the G family with the GPUs. I think this is a 16 virtual GPU. We have to install also the NVIDIA driver. Okay, I use the NVIDIA driver 535. We also need the Python at least 3.12 to make it work smoothly. So thank you so much for watching this video tutorial. I hope that you found helpful. If you have any questions or feedback, feel free to reach out. Okay, see you soon and happy coding.